So dummy variables, as I mentioned, dummy variable is one that takes the value 0 or 1 to indicate the absence or presence of some categorical effect that may be expressed to shift the outcome. Okay. If I stay in urban area, in that case, my starting point of the regression equation may be different from that of the fact that if I stay in the rural area. If I am female, my starting point may be different from a male. Okay. So this kind of thing. So it may result in shift of the regression model. So male is indicated by one layer, female may be indicated by another layer, etc. Several examples are male, female, smoker, non-smoker, as I mentioned, again, married, unmarried, educated, not educated. Okay. Once created, these proxies or dummies are used in regression analysis just like other explanatory variables, yielding standard ordinary least square results. The econometric literature abounds with the examples of use of dummy variables. The demand for specific good, for example, mineral water, may vary between urban and rural districts. Everybody understands this. The demand for labor from an industry may show seasonal variations. If you think about agriculture, in that case, you will get more seasonal fluctuations in the labor demand. So it will vary. Think about demand for umbrella. It will also vary season-wise. Think about woolen garments. It will also vary season-wise. Okay. So for a number of commodities, we will get this kind of seasonal variation in the demand. The wages paid to men and women may reveal variations, gender discrimination, gender studies, which are not be explained by variables like education, experience, skill, etc. Only because of difference in gender, we may get difference in wage rate. Okay, if I control by education, experience, skills, then also just because of gender, there are many evidence in the literature. Just because of gender, the wage may vary. Okay, so for these kind of studies, then because of different categories, we want to notify the fact that whether there is any change or not. In that case, we will go for this kind of dummy variable analysis. Now, if we look at this slide, okay, we are getting different pictures. Always we are considering two categories, male and female. Gender basically is the concerned variable. So it may happen that we are trying to measure whether age actually is indicating the experience. Okay. So as experience varies, whether wage varies or not. So in this case, we may find that the starting point of wage is different for male compared to female, or it may happen that their starting point is same. However, as experience increases, rate of growth in wage for male is greater or higher compared to that of female, or we may get both. Their starting points are different, as well as the rate of growth that is also different. Okay. In the first case, if we get for the categories, the lines are parallel, that is, they are starting from different points only, we call it intercept dummy. If the starting point is same, however, the rate of change is different, in that case, we call it slope dummy. And this is called the interaction dummy, where both the intercept as well as slopes are changing. Actually, in our analysis, we will mostly focus on the first and the third variety, because second is in between. Okay, actually we will develop our models or analyze, the first and the third varieties. The intercept dummy is also called the additive dummy, whereas the slope dummy is also called the multiplicative dummy. So intercept dummy is also called the additive dummy, and slope dummy is also called the multiplicative dummy. When we are talking about multiplicative dummy, actually we are taking care of both the second and the third cases. In case of multiplicative dummy, the starting point may be same. However, slopes should be different because our main focus in case of multiplicative dummy is the difference in slope. Okay, so in case of multiplicative dummy, the starting point may be same or starting point may differ as well. Okay, so let's first introduce the slope dummy or additive dummy. Suppose we have data on aggregate consumption and income of 1,000 individuals, 750 of whom are married and 250 unmarried. Among 1,000 individuals, there are two varieties, married and unmarried. Now, we may formulate the consumption function as, yi is equal to alpha plus beta xi plus epsilon I for all 1,000 individuals, where yi and xi refer to aggregate consumption and income of the ith individual. However, there are two groups, and as a researcher, you may be interested for the fact that whether MPC varies between the married and unmarried groups, whether marginal propensity to consume varies between these two groups. Then one may suggest that we can go for two separate regressions. That is, we will run a regression yi is equal to alpha 1 plus beta 1 xi plus epsilon I for 750 observations, and now you will be able to do it using stata command. For you can use if condition with the regression condition, So if gender equal to sorry, it's not gender, if the marital status equal to say married, you can write one equation or estimate one equation, and for the other group you may estimate another equation. Am I right, everybody? Can we do so? For two different groups, can I estimate the regression equations? Titir?
Yes, ma'am.
Can I?
Yes, ma'am.
So what is the problem? Why we need to learn about a different technique? So if I can run different equations for different groups, why we are discussing all these things? Any idea? You are telling that using if condition, we will be able to do this. So why we need to learn a technique to handle this situation? Anyone? Any idea? Please try.
To indicate absence and presence of some categorical effects.
That cannot be the interpretation, I am telling that absence and presence can be estimated using two separate regression equations. Now the question is then why we need a technique which will help us to accommodate this kind of situation, or to help us to handle this kind of situation. What can be the problem in the earlier case if we try to run separate regressions for different groups? What can be the problems? What can be the real life problem?
One variable may affect another.
One variable, yes, Naurin. Naurin,
One variable may affect another, so we may have some error in our calculation because they're affecting each other when we are calculating together.
I didn't get you clearly. Can you give an example, Naurin, and Explain what you want to indicate. Suppose there are married and unmarried, and you are running to separate equations, I am telling. So, this kind of categorical aspect can be handled using separate regression equations. So, why we need another technique, or what will be the problem if we try to run separate regression equations for separate qualitative aspects? Twinkle, you wanted to?
Ma'am, I was thinking of insufficient information.
Insufficient information. Why you are thinking about that?
We may not have the proper data regarding the consumption or the income level of the individuals.
So in that case, you will be not able to run any regression, if you do not have sufficient data on the variables you are considering. That is the general problem. You will be not able to run any regression, isn't it?
Yes,
Ma'am,
ma'am.
Yes,
can I try
yes.
once?
Yeah,
So,
definitely.
like, a single equation can like work for everyone. Like, if we done like one is zero once, and then other one is one, like that.
Actually, the problem is here I'm talking about a single categorical variable. Now, there may be multiple qualitative variables which may affect Y. Okay, for example, gender, same consumption income equation. Now, apart from income, consumption may be affected by gender, marital status, level of education of the incumbent, parental education, whether the individual belong to urban or rural area. Okay, so all this, whether the individual is a single child in the family. So there may be so many things. So if there are too many things, how many if conditions you will put? How we will run the regression in that case? Okay, so if there is that, suppose there are 25 qualitative variables, and is it possible to accommodate all these 25 varieties using the if condition? The answer is no. You will be not able to do it. So we need to learn a technique by which we will be able to manage the situation when there will be, a number of qualitative variables in the analysis. Okay. So when there will be multiple qualitative variables, if I try to estimate different equations for all these things, there will be permutation combination. And if there are 25 categorical variables, I hope you are understanding how many regressions you need to learn. Okay, then you will forget, what equation 1 is indicating, when what equation 2 is indicating. Just we will be not able to keep track of everything. Okay, for that matter, we need to learn what will be the formal methodology to handle these equations. Okay, now to begin with, we may think about, we can separately run two regressions for 750 observations and 250 observations respectively. Two conceivable situations now arise, when I'm writing these two equations, yi is equal to alpha 1 plus beta 1 xi plus epsilon I, and yi is equal to alpha 2 plus beta 2 xi plus epsilon I. Two possibilities are there. When I am moving from one group to other, the MPC is not changing. However, the starting point is changing. That is, intercept will vary. However, beta will not vary. Another possibility is both the intercept as well as the slope will vary. That is, for the married and unmarried, the starting point as well as MPC, both the things will vary. Two equations differ only in their intercepts. In that case, beta 1 is equal to beta 2 is equal to beta. Two equations differ in slope and intercept. Additive dummies can conveniently handle the first of the two situations, first of the above two situations. The two equations are written assuming a common slope then. So yi is equal to alpha 1 plus beta xi plus epsilon I. Yi is equal to alpha 2. The slope coefficient remains to be beta. These equations can be combined by introducing a dummy variable d such that di is equal to 1 if the ith individual is single, 0 otherwise. So di is equal to 1 if the ith individual is unmarried or single, 0 otherwise. So look at the combined equation. What I am doing, yi is equal to alpha 1 plus the difference between the intercepts of the two regression models. That is how the alpha 2 is varying compared to alpha 1. The difference between the two into di plus beta xi plus epsilon I. Now, if you put di is equal to 1, in that case, alpha 1 will be cancelled and you will get the equation alpha 2 plus beta xi plus epsilon I. So what I am telling, if I put the value di is equal to 1, I get the equation for the single alpha 2 plus beta xi plus epsilon I. However, if I put the value 0, I get the equation alpha 1 plus beta xi plus epsilon I, which is the equation for the married. So using the dummy variable technique, we can express both the equations in a single equations, and putting the value of the dummy variables, basically I am writing a number of equations. Now, if there are another category, say rural urban, in the similar fashion, I'll be able to add one more dummy variable for that. I'll go to that. I'll show you how to do that. Okay. So to begin with, this equation 1 is showing us how we can add the equations in a single equation. The equation 1 can be rewritten as yi is equal to alpha 1 plus delta di. Delta is nothing but alpha 2 minus alpha 1 plus beta xi plus epsilon I. Now, if you write the equation in this format, no way you are disturbing the error term in the model. Error term is classical in nature. So you will be able to estimate the equation using ordinary least square technique. So equation 2 can be estimated using OLS, considering xi and di are two regressors of the model. Delta or alpha 2 minus alpha 1 indicates the excess of intercept for single individuals over that of married. Okay, so it is indicating excess of single individual over the married. Alpha 1 is the intercept for the married. Alpha 2 is the intercept for unmarried. So it is showing us the excess of intercept. If alpha 2 is negative and alpha 1 is positive, in that case, the intercept of the second variety, that is the single individual, will be lower than that of the married group. On the other hand, if this alpha 2 minus alpha 1 is positive, in that case, you will find that the other group remains above the alpha 1 group, that means married group. Okay, so depending on the value of alpha 2 minus alpha 1, it will be decided which group will lie above and which group will lie below, like any other intercept. Finally, the value will decide. So if I write the thing in this way, we call the first group, that is the married group, as the reference category. So with respect to the reference category, we will try to check deviation of the intercept of the rest of the categories. So in a dummy variable analysis, when we will have categories, we will consider one category as the reference category, and we will try to measure the deviation of intercepts of the rest of the categories from these reference category. Similar type of model can be framed for two different time periods or two different socio-economic scenarios like war and peace, etc. The use of multiple dummies raises no new issue in principle if we introduce the sex difference along with the marital status. Equation 2 can be rewritten as yi is equal to alpha 1 plus delta 1 was there, d1i, di I am rewriting as d1i, delta 2 d2i plus beta xi plus epsilon I. Now if I put d1i is equal to 1, in that case the intercept is becoming alpha 1 plus delta 1. Okay, now there are four possibilities, since I have increased one more binary context, the gender context I have incorporated. Basically there are four possibilities. I have basically four equations, that is married girl, married boy, unmarried girl, unmarried boy, so we have four categories now. So if you look at this equation, d1i is equal to 1 means the intercept is alpha 1 plus delta 1. In that case, if I consider d2i to be equal to 1, actually the intercept will be alpha 1 plus delta 1 plus delta 2. If I put d2i is equal to 0 when d1i is equal to 1, I'll get the intercept alpha 1 plus delta 1. If I put d2i is equal to 1, however d1i is equal to 0, I'll get the intercept alpha 1 plus delta 2. If I put both d1i, d2i is equal to 0, that means if I write the equation for the female married, in that case the intercept will be alpha 1. So what I am getting for the female married, the intercept will be alpha 1. For, for suppose female single, what will be the regression equation? Female single? Anyone? What will be the...
Ma'am, can I try?
Yeah, sure.
Yi equals to alpha 1 plus delta 2 d2 plus beta xi plus epsilon I.
D2 will be not there because you are writing the value for D2 only. Either it is 0 or 1, isn't it? When you are telling that D2i is equal to 1, you are getting the intercept alpha 1 plus delta 2. D1i is equal to 0. So D2i will be not there.
Yeah, it's 1. I'm sorry, ma'am.
So it is alpha 1 plus delta 2 is the intercept plus beta xi plus epsilon I. Is it okay? So in this way, changing the values of d1i and d2i, actually we are getting equations for 4 groups. So beta is the common slope coefficient, alpha 1 is the intercept of the married females, alpha 1 plus delta 1 is the intercept of married males, alpha 1 plus delta 2 is the intercept of single females, alpha 1 plus delta 2 is the intercept of the single males. So in this way, you can go on and on. So I hope you are finding that if all the dummy variables are equal to 0, you are getting back the intercept of the original model. And this intercept is presenting one intercept of one particular category. And then adjusting that value, we are getting, the intercepts of the rest of the groups. So this alpha 1 can be considered as the reference category. And with respect to this reference category, we are getting certain changes when we are moving from one group to other. Okay. So in this way, actually, we present the intercept dummy. Now you can increase one more category here. I considered gender, I considered marital status. Now I can consider the place of residence. So I can add delta 3 D3I, where D3I is equal to 1 if the individual resides in urban area, 0 otherwise, or 0 if resides in the rural area. So in that way, if I introduce D3I, you will get, alpha 1 plus delta 2 plus delta 3 for one category. Then rest of the things will appear in the fashion as I mentioned here. So as we increase the number of dummy variables in the model, we will be able to go on and on. And in a single equation, we will be able to capture all these varieties, all these different groups very smoothly, and can estimate all the parameters using the least square technique, etc. So this is the nicety of the dummy variable. First of all, we can accommodate the attributes in the regression model. Number 2, in a single equation, we can present all these entire set of regression equations. Here, basically, there are 4 regression equations. Equation 3 is presenting briefly 4 models. Now, if I increase another variety, another dummy variable, as I mentioned, urban, rural, again, in equation 3 only, I'll be able to incorporate that. Again, if I incorporate another binary dummy variable like educated, not educated, that also I'll be able to accommodate in equation number 3. So I can go on, and I can use a single equation to indicate, 16, 20, 40 regression models. So this is the specialty of the dummy variable technique. We have 2 gender categories, but look at this note specifically. We have 2 gender categories. Again, in case of marital status also, we have 2 marital status. However, we are using a single dummy variable. Whenever I am introducing a particular dummy variable, say marital status or gender, there are 2 categories. However, I am indicating a single dummy variable D1I. To indicate the other variety, I am using another variable D2I. However, I am not using 2 different dummy variables for 2 different categories. Here also, I am not using 2 different dummy variables to indicate 2 different categories. So if there are 2 categories, I am using one single dummy variable. You will find that if there are 3 categories, primary, secondary, higher secondary, in that case, we will use 2 dummy variables, 2 binary dummy variables. Okay. In other words, if there is an intercept in the regression model, in that case, we use one dummy less compared to the number of categories we have. I'm repeating, in case of dummy variable analysis, if I have two categories, I use one dummy variable. If I have three categories, I use two dummy variables. If I have five categories, in that case, I use four dummy variables. So number of dummy variables we use with respect to categories of a particular qualitative variable, that is one less than number of categories we have in the model. If I consider the number of dummy variables exactly equal to number of categories for a particular qualitative variable, in that case, we face a problem of dummy variable trap. So in the next part, we will like to understand what is the meaning of dummy variable trap. Okay, to understand this, first tell me whether you are understanding this equation or not. Everybody is understanding this? How to incorporate a number of dummy variables to generate different intercepts and thereby different groups? Is it okay to all of you?
Yes, ma'am.
Sraya, is it understandable?
Yes, ma'am.
Very good. Okay, so let's go back to equation number 2. This is equation number 2, where we have a single dummy variable, yi is equal to alpha 1 plus delta di plus beta xi plus epsilon I. That is, we have the category marital status here. So what I'm telling that, let's consider equation 2. Let's consider two dummy variables for marital status. D1I is equal to 1 if the individual is single, 0 otherwise. Again, D2I is equal to 1 if the individual is married, 0 otherwise. So I am defining two dummy variables for two categories, D1I and D2I. D1I is equal to 1 is indicating the individual is single. D2I is equal to 1 indicates the individual is married. Here, D1I plus D2I is equal to 1 because either these are two mutually exclusive categories. So if the individual is single, in that case, the individual is not married. So D2I will be equal to 0. And if D1I is equal to 0, in that case, D2I is equal to 1. So mutually exclusive position. So we can safely write D1I plus D2I is equal to 1. So together you cannot have D1I is equal to 1 and D2I is equal to 1. So D1I plus D2I is equal to 1 for all I. Hence, instead of equation 2, we have yi is equal to alpha plus delta 1 D1I plus delta 2 D2I plus beta xi plus epsilon I. So if I like to write the X matrix will be 1, then dot, 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 dot. Actually, there will be vertical dots. There are n observations. Okay, so 1, 1, dot, dot, then 1, x1, x2, dot, dot, vertically, then xn, d11, d12, it will move up to d1n, d21, d22, it will move up to d2n. Now, if I add columns 3 and 4, in that case, the value is equal to 1 because mutually exclusive. The binary category is mutually exclusive. So D1I plus D2I is equal to 1. So what we will find that the first column, that is the column we have for the intercept terms, 1, 1, 1, 1, 1, will be similar to that of D1I plus D2I. Okay. And in that case, we will face the problem of singularity. We will be not able to derive determinant of x, determinant of x is basically 0. So we will be not able to calculate x prime x inverse. So we will be not able to present our beta hat OLS, because beta hat OLS is x prime x inverse x prime y. So this is the problem, okay? This is the problem here. This particular problem is known as dummy variable trap. So never consider the categories, dummy variables exactly equal to the categories you have in the qualitative variable. If the categories you have in the qualitative variable is 10, in that case, you have to define 9 binary dummies. If the number of categories is 3, in that case, 2 binary dummies. If the number of categories is equal to 2, in that case, 1 dummy variable. Okay? However, remember that if the model does not have the intercept term, I am repeating, if the model does not have the intercept term, in that case, the number of dummy variables will be exactly equal to number of categories you have. Here, when you are considering the 0 category in equation number 2, actually the intercept is giving you, the original intercept is giving you the intercept of one particular group. However, if originally in the equation you do not have any intercept, in that case you have to define the number of dummy variables which will be exactly equal to number of categories. So let's go back to equation number 2 once again. Since you have alpha 1 here, when you are considering di to be equal to 0, you are getting the intercept to be alpha 1. However, if there is no alpha 1 to begin with, if the equation does not have the intercept term, in that case, the number of dummy variables will be exactly equal to number of categories. Okay. In general, there will be intercept in the regression model. So in general, you have to define number of dummies that will be number of categories less 1. Otherwise, you will face the problem of dummy variable trap. Any question regarding the dummy variable trap? Okay, so I'll tell you to write one equation using the intercept dummy, Suppose this is the model. D1I is equal to 1, individual is male, female, single, married, etc. Now I am considering one education dummy. So please write equation number 3 in your copy. Yi is equal to alpha 1 plus delta 1 d1i plus delta 2 d2i plus beta xi plus epsilon I. Please write down this equation. Okay, so d1i is equal to 1 if single, I think, Taina?
I'm male, female. I'm D1I male, female.
Oh, D1I male female? Okay. No problem, Okay, I'm changing. Is it now okay? So now I'm telling you to consider three educational categories. Three primary, secondary.
Ma'am,
Hmm.
ma'am, we will not incorporate the term beta xi.
Yeah, definitely we will. So this is the idea. Now I am telling you to incorporate three educational categories: primary, secondary, and higher secondary. Okay. Beta will remain unaltered across different groups. So, rewrite the equation and tell me how you accommodate these three educational categories using binary dummies. Using binary dummies. First of all, for three educational categories, how many dummy variables we will consider?
2.
Everyone, we need to have
Yes, ma'am.
two dummy variables. Okay, so very good. So let's define D3I is equal to 1, 0 otherwise, and D4I is equal to 1 if actually what we are finding that when both D3I is equal to D4I is equal to 0, in that case we are getting another category, that is we are getting
HS.
HS. Very good, we are getting the HS group. Okay, so this model will be rewritten as then okay. So when all the dummy variables are equal to 0, that is D1I is equal to 0, D2I is equal to 0, D3I is equal to 0, and D4I is equal to 0, we are getting the intercept to be alpha 1. And what is that group? What is that group when all dummy variables are equal to 0? Anyone? Yeah. What is that group when all four dummy variables are equal to 0?
Married female HS.
Female?
HS.
Yes, married female HS. We are getting the group or the estimation of consumption which is for married female HS. And in the similar fashion, now we will be able to consider different combinations and you will get all together all the different possible equations, So this is the style of intercept dummy. So in a single equation, now you can consider another variable having, say, another 4 categories. So you will be able to introduce 3 dummy variables and you will be able to do that. Okay, so here basically married or female married HS is the reference category. Okay, for which the intercept is alpha 1. This is the reference category. And if I get alpha 1 plus delta 1, in that case, you know, D1I is equal to 1 means male. For the male married HS, we are getting the intercept and we will be able to compare these two intercepts. Then if we D1I is equal to 0, however D2I is equal to 1, we consider the intercept. I'll be able to compare that group with the reference category. So in this way, we will proceed. How the changes are taking place when we are moving from one group to other. However, we are estimating a single equation only. We are not estimating thousands equation to understand what will be the consumption pattern for different groups. I am estimating a single equation. So this is all about the intercept dummy. Next, I'm introducing the multiplicative dummy. In case of multiplicative dummy, we are again starting with the equations, for 750 and 250 observations, 750 married individual and 250 single individuals. We introduce a dummy variable di, which is equal to 1 if the ith individual is single and 0 otherwise. Okay. Along with this, we introduce another new dummy variable w, which is equal to dx. So look at the nature of the dummy variable. It is d into x. Okay, so I'm introducing a dummy variable w, which is d into x. Okay, so we are writing the equation as yi is equal to alpha 1 plus delta 1 d1i. We are familiar with delta 1 d1i. Then we are putting the beta 1 xi, that is the MPC of the 750 observations, beta 1 xi, plus I'm bringing delta 2 wi, delta 2 wi. Okay, for the intercept dummy, we are considering delta 1 d1i, whereas for the slope, difference in slope, we are considering delta 2 wi. Delta 1 is alpha 2 minus alpha 1, difference between the two groups. Always the base category will be the intercept, So alpha 1, alpha 2 minus alpha 1, here we are considering. And, delta 2 will be in the similar fashion, beta 2 minus beta 1. Delta 1 is alpha 2 minus alpha 1, delta 2 is beta 2 minus beta 1. Now let's put the values and let's try to understand what we are basically getting. Okay. So, when, when I am putting di to be equal to 1, I'll request you to write down the equation. Suppose di is equal to 1. The equation is becoming yi is equal to alpha 1 plus delta 1 plus beta 1 xi. Intercept is alpha 1 plus delta 1. Then beta 1 xi now the value of, what will be the value of w in this case?
And xi.
Xi. So how we will present the thing?
Beta
plus
1
delta 2. Yes, Rudra. Yes, try.
and beta 1 plus beta 2 xi. Sorry, beta 1 plus delta 2 xi.
Yeah. So intercept is alpha 1 plus delta 1 then, and slope is beta 1 plus delta 2. Now what is delta 2? Beta 2 minus beta 1. So basically what it is? Beta 2. First you write down when d1i is equal to 1, the equation is becoming yi is equal to alpha 1 plus delta 1 plus beta 1 plus delta 2 into xi plus epsilon I. Now what is delta 2? Delta 2 is nothing but beta 2 minus beta 1. So basically what you are writing, that is beta 2. And delta 1 is alpha 2 minus alpha 1. So basically you are writing alpha 2 plus beta 2 xi plus epsilon I. However, when you are putting di is equal to 0, your intercept is alpha 1 and you are getting beta 1 xi because your d into x is equal to 0 plus epsilon I. So you are getting back the first equation. So when you are putting di is equal to 1, you are getting back the second equation. When you are putting di is equal to 0, you are getting back the first equation. So in this way, we can incorporate the change in intercept as well as the change in slope in a single equation. And when we consider a change in slope, we call it a multiplicative dummy because look at the structure of the dummy variable. It comes in the form d into x. Therefore, we call it multiplicative dummy. Any question?
Ma'am, can you please explain again?
How you are getting back to equations?
Yes, ma'am.
Okay. So would you please write down the equation number 5 in your copy? Equation number 5 is yi is equal to alpha 1 plus delta 1 d1i plus beta 1 xi plus beta 2 wi plus epsilon I. Then set di is equal to 1 in the following structure. Di is equal to 1. Equation becomes yi is equal to alpha 1 plus delta 1 plus within bracket beta 1 plus delta 2 into xi plus epsilon I. Because wi is equal to xi then when d is equal to 1. I'm repeating, your equation is becoming yi is equal to alpha 1 plus delta 1 plus within bracket beta 1 plus delta 2 into xi plus epsilon I. You got it?
Yes, ma'am.
Okay. Now you look at this equation. You look at this equation, You are writing alpha 1 plus delta 1. Now what is delta 1? Alpha 2 minus alpha 1. So if you put the value of delta 1, which is alpha 2 minus alpha 1 will be cancelled. You will simply get alpha 2. Am I right?
Yes, ma'am.
Then what you have? Beta 1 plus delta 2. Now if you put the value of delta 2, this is beta 2 minus beta 1. So you have beta 1 plus beta 2 minus beta 1. So you can cancel beta 1. So you are left with beta 2 only. So when you are putting di is equal to 1, you are getting back the equation number 2. yi is equal to alpha 2 plus beta 2 xi plus epsilon I. Am I right?
Yes, ma'am.
Okay. Now you put di is equal to 0. It's very easy. Yi is equal to alpha 1 plus beta 1 xi plus epsilon I. Are you getting it? Put d1i is equal to 0, and for that matter w is also equal to 0. So you are getting the first equation, yi is equal to alpha 1 plus beta 1 xi plus epsilon I. Got it?
Yes, ma'am.
So I hope you are now understanding how equation 1 and 2 can be accommodated in a single equation like equation number 5.
Yes, ma'am.
Okay. Anyone else, any other question? Okay, so I'm not considering this one, you know. So look at the examples, in Madala's book, because it has been written very lucidly. The and you will get a number of examples how they are incorporating the intercept dummies, slope dummies for different categories. In case of slope dummy, I discussed about a single category. Now you can consider a multiple categories as well. However, the style will be very similar to that of the intercept dummy. Okay. So three things are important here: notion of additive dummy, notion of multiplicative dummy, and the notion of dummy variable trap. What will be the exact number of dummy variables you will consider for explaining categories of a qualitative variable? Okay. So I'm giving you an exercise, please write down this. The following regression was estimated from the following regression was estimated from 16 quarterly observations. 16 quarterly observations. YT is equal to 70.7 minus 0.90 xt plus 0.43 S1t plus 6.55 S2t minus 2.83 S3t. Okay. T ratios are in parentheses: 3.7, then 0.27, then 3.37, then 3.40, then 3.37. R square 0.68. So this is the model. We are considering T ratios in the parenthesis. Okay, students, T ratios are there in the parenthesis. Then add where SIT is equal to 1, SIT is equal to 1 in the ith quarter, SIT is equal to 1 in the ith quarter, 0 otherwise. Okay. Question is, explain the implied pattern of seasonal variation. Explain the implied pattern of seasonal variation. And interpret the result. Explain the implied pattern of seasonal variation and interpret the result. So I hope you are understanding, since the intercept is there and 3 seasonal dummies S1T, S2T and S3T are there. Basically, we are talking about 4 seasons, or we are talking about 4 quarters indicating 4 seasons, 4 seasonal dummies. So you have to write the equations for the first, second, third and the fourth quarter. Okay, so you need to write the equations for the first, second, third and the fourth quarters. Okay, so start with the first quarter. Look at the dummy variable SIT. SIT is equal to 1 in the ith quarter, 0 otherwise. That is when you will consider the first quarter, the value of SIT should be considered to be 1, 0 otherwise. So what will be the regression model for the first quarter? Anyone?
$70.7 minus 0.90 xt plus 0.43.
Okay, so what we will do, actually we will bring 0.43 with the intercept, isn't it? Because we are considering the change in the intercept.
Yes.
Okay, so we will consider first season equation will be YT is equal to 70.7 plus 0.43. This will be the intercept minus 0.90 xt plus xt, sorry. This is the estimated equation, so there is no error. This will be the equation for the first quarter. Anyone else for the second quarter? What will be the model?
70.7 plus 6.55.
70.7 plus 6.55
Minus 0.90 xt.
0 xt. Very good. What will be the equation for the third quarter? Anyone else?
Ma'am, 70.7 minus 2.83
Minus 2.83
minus 0.90 xt.
Very good. And what will be the equation for the last season, fourth quarter? Anyone?
Ma'am, 70.7 minus 0.90 xt.
Very good. Okay. So these are the things. Now, once you get this thing, you will be able to indicate, highest intercept you are getting in the second season. Okay. So you are getting actually the set of parallel lines here. You are getting this kind of set of parallel lines here. Okay. So highest intercept you have in the second season. Okay. So, this is the second season. Graph, and that is followed by the first season. So, this one is for the first, and this one is for the fourth, and the curve with the lowest intercept is for the third. Okay, so in this way we can generate a set of parallel lines using this kind of intercept dummies. Here basically we have used the intercept dummies, and we can generate a set of parallel lines here, and the interpretation will be like this. So I hope you are understanding the matter. Okay, now if you look at this equation, and if we go for a kind of stability analysis, whether season wise there is stability, etc., and we find the model is unstable. Now looking at the t statistic of the dummy variable, we will be able to understand what is the reason of instability. So if we find that the t statistic is statistically significant, we are understanding there will be a significant jump or significant change in that season. If the t ratio is insignificant, in that case we will understand there will be no variation. So in case of chow test, we can only mark whether the situation is stable or not. Here we will be able to understand, if suppose with S1T, if I get the T statistic insignificant, here it is greater than 3, so significant. However, if I get it is less, we will understand the first season and the fourth season, they will behave in the similar fashion. However, there will be a fluctuations in the second and third. Or if I find, all three seasons are giving me statistically significant T, in that case, we have to understand with respect to the first season, there will be sufficient variation in rest of the quarters or rest of the seasons, okay? So if I find, and everything will be comparable with respect to the reference categories. So the fluctuation I can measure with respect to the reference category. Okay, now here for the parallel lines, when we will prepare the write-up with respect to the fourth season only, we will be able to explain everything. With respect to the fourth season, whether the intercept of the first and the second is higher, and third is lower, etc. The explanation will be like that, So everything will be done with respect to the reference category.
Ma'am?
Yes. Yes, go
Ma'am,
on.
the intercept of the quarter is greater than first quarter. Am I correct?
Intercept?
Intercept of the third quarter is greater
Yes.
than the intercept of the first quarter.
Intercept of the third quarter. Intercept of the third quarter is 70.7 minus 2.83. So it is 2.83 less.
Oh, I have missed the minus sign. Okay, sorry, ma'am.
Okay. Okay. So in this particular case, what is the reference category? What is the reference category in this particular case?
On the fourth quarter.
Yeah. Fourth quarter. So the model having the original intercept is considered as the reference category. Now in Stata, when you will go to the practical class, you will find that if you do not tell anything to the software, it is also always considering the category having the lower denomination as the reference category. For example, if I consider one dummy here, and if I consider married, unmarried, where say unmarried is equal to 0, in that case, unmarried will be considered as the reference category. Now, if I bring another variable urban, rural, in that case, if I mark urban as 0, in that case, unmarried urban will be considered as the reference category. So the category having the lowest denomination will be considered as the reference category in Stata. However, using the generate variable commands, you can generate all the categories as a variables, and you can define the category which you will consider as the reference category. Okay, so you will learn all these things in the next class. Therefore, I stopped Richard to explain all these things. So what I am telling that in dummy variable analysis, always the analysis will center around the reference category. With respect to reference category, we need to mark the changes with respect to intercept, with respect to slopes, etc. In Stata, the category having the lowest denomination will be considered as the reference category. However, using the generate variable commands, you can generate all the categories as variables. You can generate a number of variables, which will indicate different categories. In that case, you can choose the category which you will make the reference category. For example, suppose you are generating variable married, unmarried, two variables, okay, and you then can choose whether you will consider unmarried as the reference category or married as the reference category, okay. So you need to learn all these techniques. Okay, then I told you to do some problems on chow test. Anybody tried? Anyone tried? I sent you several problems. কি কেউ চেষ্টা করেছো? Yes, Tuba? Orkodip? Orkodip, you tried?
No, ma'am.
I sent you some problems that you find. 4 point, I think 4.1 or something. So, so look at these problems. Tomorrow morning, I'll do that. I'll discuss numerical exercises both on chow test and the dummy variables, techniques, combining the things, So you will find that in your homework. The second problem covers both the chow test and the dummy variable. Probably I'll discuss that thing in the class. Rest you have to do on your own, and if there is any difficulty, in that case I'll help you. So today night, please check the problems, check the numerical exercises, and tomorrow morning I'll discuss this. Now before moving to those issues, now I'll like to say something regarding the large sample. You did something related to the large sample at your undergraduate course. However, maybe you didn't do the entire thing, or for some of the students, it may happen that at the undergraduate level, they didn't do the large sample case, However, we need to know something about the large sample, and therefore, you need to understand what is happening in case of large sample, okay? So now I'm moving to the large sample. Now, large sample means when the sample is moving towards infinity, or which is the population. So in this case, all the properties becomes the limiting properties. Okay, limiting properties, limit n tending to infinity. Okay. In case of large sample, we do not consider unbiasedness and the minimum variance property. Rather, we concentrate on consistency and the efficiency of the estimators. Okay. So at your undergraduate level, everyone learned about consistency, efficiency, etc. You know the sufficient conditions for consistency, etc. So please check all these definitions. All these things are included here. So please check the definition of consistency, efficiency, etc. from any statistics book. Okay, preferably Gulgupta, Dasgupta. In case of large sample, we will not use OLS as method of estimation. OLS is the proper method of estimation in case of finite sample. Okay, in case of large sample, we have to move for iterative method of estimation. Generally, we will use the maximum likelihood estimation technique. Okay, so we will use the maximum likelihood estimation technique. Now, in case of least square technique, we do not need to know what will be the distribution of the error terms. When we want to apply the least square technique, okay, we don't need any information on distribution of UI, of the error term. We do not need information. The information on distribution of the error term is required only when we move for hypothesis testing, when we are using the finite sample. However, if I need to use maximum likelihood estimation technique from the very beginning, we need to know what will be the distribution of the error term. Without the knowledge of distribution of the error term, we will be not able to frame our likelihood function. Everybody is aware about maximum likelihood estimation technique. You did it at your undergraduate level. We need to define a likelihood function and then we need to maximize it. Okay. So if differentiable, if it is not differentiable, in that case, in some other means, we like to increase the value, etc. Okay. Under most of the circumstances, it will be differentiable. However, there may be certain circumstances where we will not get a likelihood function which is differentiable. Okay. So the most important point in this case is, to begin with, we need the information of the distribution term. In our regression model, it is not at all a problem because already we discussed about the distribution of the error term. We have a knowledge that error is distributed normally with expectation of UI is equal to 0 and variance of UI is equal to sigma square IN. So we are considering this context. So considering this context or this distribution of the error term, we need to know how, using maximum likelihood estimation technique, we can derive the values of the parameters in the model. How we can derive the estimated value of the sigma square, because that is also very important. Along with the estimation of the parameters of the model, we also need to consider the estimation of the variance of the error term, because under most of the circumstances, the variance of the error is unknown. Okay. So the likelihood analysis requires large sample, or in case of large sample, we will use the maximum likelihood estimation technique. Likelihood analysis is based on the knowledge of distribution. So to begin with, we need the information on yt given xt, what distribution it is following. Okay. As I mentioned, U is following the normal distribution with mean 0, basically 0 vector, and the variance covariance matrix is given by sigma square I. And here we are presenting the multivariate normal density of U, which is given by 1 by sigma root over 2 pi, or to the power n, because it is a multivariate model. Or you can write this thing as 1 by 2 pi sigma square whole to the power n by 2. You can either write root, then whole to the power n, or you can present the thing as 2 pi sigma square whole to the power n by 2. E to the power minus half. In the denominator, there is sigma square. And in the numerator, we have u prime u. What is the standard style of writing the normal distribution? 1 by sigma root over 2 pi e to the power minus half x minus mu by sigma square. Here we are finding minus 1 by 2 sigma square part as it is. However, x minus mu whole square has been replaced by u prime u. Instead of considering the distribution of x, here we are considering the distribution of u. So it should be, ui minus u bar whole square kind of thing. Now u bar is expectation of ui, that is equal to 0. And whole square in terms of matrix notation comes in the format u prime u. So xi minus mu whole square, that has been replaced by u prime u. So this is the format of the multivariate normal density for the error term ui, or u vector. The multivariate density for y conditional on x is then f of y given x equal to f of u multiplied with the Jacobian transformer. This is the Jacobian transformer, because from the u we are presenting the y space, so we need a Jacobian transformer. So it is det del u by del y. This is the Jacobian transformer, where determinant del u by del y is the absolute value of the determinant formed from n by n matrix of partial derivatives of the elements of u with respect to elements of y. All partial derivatives, del u, del y, we are considering. The log likelihood function, generally, if it is a normal function, exponential to the power something is there, we will go for the log likelihood function, because that will be linear in parameters, So we are considering L, which is ln of f of y given x, which is equivalent to ln of f u, that is minus n by 2 ln. If you can remember this equation, we are writing this equation actually. minus n by 2 ln 2 pi minus n by 2 log ln sigma square. Two terms were there. So minus n by 2, I'm breaking it into two parts because I need to find out differentiation with respect to sigma square. However, pi is a constant, so I'm separating out sigma square from 2 pi. Then minus 1 by 2 sigma square u prime u. This part, log e is equal to 1. So if I adjust this term, I am getting minus 1 by 2 sigma square u prime e. Actually, there is ln e. Ln e is equal to 1. Therefore, I am not writing it. So this can be rewritten as minus n by 2 ln 2 pi minus n by 2 ln sigma square minus 1 by 2 sigma square and y minus x beta transpose y minus x beta. Then I have to take partial derivatives with respect to beta and sigma square to derive the estimated values of beta and sigma square. Okay, so taking the partial derivatives with respect to beta and sigma square, we derive the estimated values. Beta hat is equal to x prime x inverse x prime y, and this is equal to y minus x beta hat prime into y minus x beta hat by n. So it will be very, very similar to the least square values. However, in the sigma hat square, generally in the denominator we find n minus k. However, here we are getting n. Actually, when we consider a large sample, there is no difference between n and n minus k. Okay, n is tending towards infinity. So the only difference between the least square estimators and MLE estimator is the denominator of sigma hat square. However, we are understanding here we are using the limiting property and therefore we are getting these values. Okay, now to understand how we will really get these values, I'm considering a simple model, and in the note, simple regression model. Okay, and I basically considered the likelihood function, and then I have taken derivatives with respect to two parameters alpha and beta, not with respect to the entire beta vector, because this will be easier for your understanding. So take derivative of ln L with respect to alpha beta, and you will get the values for alpha hat, beta hat, and you will find that these are similar to that of OLS. Actually, you are getting the same normal equations. So solving this, you will get the same values. However, when you are taking differentiation with respect to sigma u, you are trying to find out the value of sigma u hat square. You are getting this to be RSS by n. So the above things which I claimed, here, the OLS estimators will be, the estimated values will be similar to that of OLS, and sigma hat square value numerator will be similar. However, there will be a change in the denominator that you will be able to understand if you solve this part. Many of you did it at your undergraduate level only. Those who didn't do, please check the steps and do the things. You will understand that you are getting back the OLS estimators. Okay, then I'm mentioning that ML estimators are consistent. Here we will not talk about the unbiasedness. ML estimators are asymptotically normal. In case of least square, we say that beta hat is normally distributed. Here I'm telling asymptotically normal because in all the cases, I have to keep in my mind n is tending towards infinity. So asymptotic things are coming. Okay, so these things are important. And finally, the most important things are what kind of tests we use in context of large sample. That is the likelihood ratio test and world tests. These tests are important. You found that while we discussed about the finite sample, we talked about OLS, we talked about T statistic as well as F statistic. To check the significance of a single coefficient, we use T, whereas when we consider the overall significance, generally we use F statistic. However, there is some link between T square and F, etc. that you did. When you will move to the large sample, you will find that most of the tests are based on chi-square distribution. Okay, so here you will get chi-square distribution. We can use likelihood ratio test, we can use Wald test, everything you will find that are based on chi-square distribution. Okay, so mark that change, and you also need to understand what is the meaning of likelihood ratio test, what is the meaning of this Wald test, and what is the meaning of LM test, Lagrange multiplier test. And this comparison is also there in your syllabus, how we can compare these three tests and establish the relationship. The Wald test is greater than equal to the likelihood ratio test, and that is greater than equal to LM test. Did you check all these notes I sent to you? If anyone have any query regarding any step or has some problem regarding understanding of these tests, I can answer to your query. Anyone, any question? First of all, anyone checked this thing? Ujan?
Yes, ma'am.
Or Kudeep, you checked? Okay.
Yes.
So, my question is, are you understanding all the steps? Here also we are considering the restricted equations, unrestricted equations. We are considering the residual sum of squares of the restricted model, unrestricted model, considering the ratio of the two. And then we are explaining how this ratio after certain adjustment will follow the chi-square distribution. Okay. In case of Wald test, it is used. Wald test is basically the normal distribution test. It is more like tau. Okay. So it is the normal distribution based test. So in case of Wald test, how we are changing the technical things little bit, because if it is a large sample, everything will follow the normal distribution following the central limit theorem. Okay, I hope everyone is aware of central limit theorem. So if it is a large sample, ultimately you can start with T distribution, you can start with any distribution. Finally, it will move towards, in fact, we learned binomial Poisson, everything will move towards the standard normal distribution. So if it is a large sample, everything at a limit or every distribution at a limit will follow the normal distribution. So when we will go for coefficient wise testing in case of large sample, we use the Wald test, which is based on standard normal distribution. Okay. We have also introduced the Lagrange multiplier test that is also used in case of large sample. LR test and LM test, these are mainly used for checking overall significance of the model. Therefore, it is based on restricted and unrestricted model and try to understand whether there is any significant difference between the restricted and unrestricted model or not. Okay. Whereas the Wald test, that is based on the normal distribution, standard normal distribution, and it checks whether individual coefficients are significant or not. And you will find that all these distributions ultimately can be presented in terms of R square, all these distributions can be presented in terms of R square. So this is the formula by which you will be able to compare all these three tests. So here I am showing LR is following in ln 1 by 1 minus R square. Then I talked about the world test, and you will find that it is nr square by 1 minus r square. Finally, I talked about the Lagrange multiplier test, which is nr square. So it is nr square, it is nr square by 1 minus r square. It is, the first one was n into ln by 1 minus r square. So finally, what we need to do, we need to compare between the world test, Lagrange likelihood ratio test, and Lagrange multiplier test. And using these steps, we can show that W is greater than equal to LR greater than equal to LM. So everything is technical unless you look at it, you will feel that it's very difficult, whatever. It's not that difficult. And I have written everything in a simplified manner. So I hope if you go through these things, you will understand the steps. Anyway, if anyone have any query. Is it okay?
Yes, ma'am.
Okay, for large sample, you can expect conceptual question. We will not do any numerical exercise. For chow test, etc., we will do some numerical exercise. However, for these, we will not do. Okay, so next, after completing this thing, actually, in the next step, we will have the regression diagnostics. The regression diagnostics, we will divide into two parts. In the first part, we will consider several aspects related to X. Among the several aspects, our focus will be on omitted variables. If there are several omitted variables in the analysis, what will be the problem? Or if I have some extraneous information in the model, if I have several X variables which are not that important, whether there will be any problem in the regression model or not, there will be any bias or not. So that we need to know. If we have very important variables we miss, what will happen? If we keep extra variables, what will happen? Then we need to know the issue related to multicollinearity. Now, when I talked about the assumptions in a regression model, multiple regression model, I mentioned that all the columns of X should be independent to each other. However, in reality, when we find out the observations on each of the explanatory variables, under many circumstances, we find that columns are interrelated. So when the columns are interrelated, how we will detect that? If the columns are interrelated, what are the consequences and what are the remedies that we need to learn? That is the aspect of multicollinearity we need to learn. Thirdly, another important problem is misspecification. Suppose the model you are considering X, however, you actually need to consider X square, or you are not considering any lag. However, basically, if you want to estimate the demand equation, suppose you need the lag. So under many circumstances, we misspecify the model. The actual theory is something, or data is trying to explain something. However, we are misspecifying the model. Okay. So this is another issue related to X variable. Then there are issues related to U variables. The very stringent assumptions we make regarding the U variables. One is the homoscedasticity, another is the non-autocorrelation. However, when we consider the real life situation, it is very difficult to get a situation which is homoscedastic as well as non-autocorrelated. So we need to learn what are the consequences of heteroscedasticity if the variances are heterogeneous of the disturbance term. What will be the consequences? What can be the detection method? And what will be the remedies? Similarly, in presence of autocorrelation, what are the consequences? What can be the method of detection? And what will be the remedial methods? So for these two, most of you or all of you did something at least at your undergraduate level. All of you did something related to heteroscedasticity as well as autocorrelation. So what happens in case of heteroscedasticity? What happens in case of autocorrelation? In case of autocorrelation, what is the meaning of Darwin-Watson test statistic? How we detect autocorrelation, presence of autocorrelation using the DW test statistic, etc. I think all of you did. Am I right? All of you did it at your undergraduate level?
Yes, ma'am.
Rest of the students, Titir,
Yes, ma'am.
Twinkle, Sraya,
Yes.
Kudeep, Nazma.
Yes, ma'am.
Yes, ma'am.
Okay, so all of you did this thing.